Today we are going to talk about three-phase alternators. This includes principles of three-phase alternators, the rotor, the brushless, the Jepperling alternator sharing the load field discharge protection. So let's get started. Most of the electrical power in the world today is produced by alternating current generators, or alternators. Electrical power companies use alternators rated in gigawatts. A gigawatt equals 1 million watts. The entire North American continent is powered by alternating current generators connected together in parallel. These alternators are powered by steam turbines. The turbines, called prime movers, are powered by oil, coal, natural gas, and/or nuclear energy. Three-phase alternators operate on the principle of electromagnetic induction as direct current generators, but they have no commutator to change the alternating current produced in the armature into direct current. These are two basic types of alternators, the revolving armature type and the revolving field type. Although there are some single-phase alternators that are used as portable power units for emergency home use, or to operate power tools in a remote location, most alternators are three-phase. Revolving armature type alternators read least use of the two basic types. This alternator uses armature similar to that of a direct current machine, with the exception that the loops of wire are connected to slip rings instead of to a commutator. There are three separate windings, which are connected in either delta or Y configuration. The armature windings are rotated inside a magnetic field. Power is carried to the outside circuit via brushes riding against the slip rings. This alternator is the least used because it is very limited in the amount of output voltage in kilovoltamps or kVA capacity it can develop. Revolving field type alternators use a stationary armature called the stator and a rotating magnetic field. This design permits higher voltage and kVA ratings because the outside circuit is connected directly to the stator and is not routed through slip rings and brushes. This type of alternator is constructed by placing three sets of windings 120 degrees apart. The rotor is the rotating member of the machine. It provides the magnetism needed to induce voltage into the stator windings. The magnets of the rotor are electromagnets and require some source of external direct current to excite the alternator. This direct current is known as excitation current. The alternator cannot produce an output voltage until the rotor has been excited. Some alternators use slip rings and brushes to provide the excitation current to the rotor. A good example of this type of rotor can be found in the alternator of most automobiles. The DC excitation current can be varied in order to change the strength of the magnetic field. The brushless excitermos large alternators use an exciter that contains no brushes. This is accomplished by adding a separate small alternator of the armature type on the same shaft of the rotor of the larger alternator. The armature rotates between wound electromagnets. The DC excitation current is connected to the wound stationary magnets. The amount of voltage induced in the rotor can be varied by changing the amount of excitation current supplied to the electromagnets. The output voltage of the armature is connected to a three-phase bridge rectifier mounted on the rotor shaft. The bridge rectifier converts the three-phase AC voltage produced in the armature into DC voltagabor. It is applied to the main rotor windings. Since the armature, rectifier, and rotor windings are connected to the main rotor shaft, they all rotate together and no brushes or slip rings are needed to provide excitation current for the large alternator. Alternator cooling. There are two main methods of cooling alternators. Alternators of small kVA ratings are generally air-cooled. Open spaces are left in the stator windings, and slots are often provided in the core material for the passage of air. Air-cooled alternators have a fan attached to one end of the shaft that circulates air through the entire assembly. Large capacity alternators are often enclosed and operate in a hydrogen atmosphere. There are several advantages in using hydrogen. Hydrogen is less dense than air at the same pressure. The lower density reduces the windage loss of the spinning rotor. A second advantage in operating an alternator in a hydrogen atmosphere is that hydrogen has the ability to absorb and remove heat much faster than air. At a pressure of 1 atmosphere, hydrogen has a specific heat of approximately 0.238. This means the hydrogen has the ability to absorb approximately 13.8 times more heat than air. Frequency output frequency of an alternator is determined by the factors number of stator poles and speed of rotation of the rotor. Since the number of stator's poles is constant for a particular machine, the output frequency is controlled by adjusting the speed of the rotor. Output voltage factors determine the amount of output voltage of an alternator, the length of the armature or stator conductors, number of turns, the strength of the magnetic field of the rotor, and the speed of rotation of the rotor. Only of the factors that determines the amount of induced voltage is the length of the conductor. This factor is often stated as number of turns of wire in the stator because the voltage induced in each turn adds. Increasing the number of turns of wire has the same effect as increasing the length of one conductor. Paralleling alternator. Since one alternator cannot produce all the power that is required, it often becomes necessary to use more than one machine. When more than one alternator is to be used, they are connected in parallel with each other. Several conditions must be met before parallel alternators can be used. First, the phases must be connected in such a manner that the phase rotation of all the machines is same. Phases A, B, and C of one machine must be in sequence with phases A, B, and C of the other machine. Determining rotation. Most common method of detecting when the phase rotation of one alternator is matched to the phase rotation of the other is with the use of lights. The synchroscope. Another instrument often used for paralleling to alternators is the synchroscope. It measures the difference in voltage and frequency of the two alternators. The pointer of the synchroscope is free to rotate in a 360-degree arc. The alternator already connected to the load is considered to be the base machine. Sharing the load. After the alternators have been paralleled, the power input to alternator 2 must be increased to permit it to share part of the load. For example, if the alternator is being driven by steam turbine, the power of the turbine would have to be increased. When this is done, the power to the load will remain constant. The power output of the base alternator will decrease, and the power output of the second alternator will decrease. Field discharge protection. When DC excitation current is disconnected, the collapsing magnetic field can induce a high voltage in the rotor windings. This voltage can be high enough to arc contacts and damage the rotor windings or other circuit components. One method is preventing the induced voltage from becoming excessive is with the use of a field discharge resistor. Thank you, and please like, share and subscribe.